Okay, let's look at example on chapter 7, and this is I will look at a flow over a cylinder. Like we have external flow at u infinity equal to 5 meters per second over a cylinder with a diameter of 0.02 meters, and this cylinder is an infinitely long cylinder, so it's going into the page and outside the page, and the surface of the cylinder is at a constant temperature of 400 Kelvin, and the surrounding air that's blowing over it is at a temperature of 300 Kelvin. So basically it's in ambient conditions, and we'll assume that the surface temperature of this particular cylinder does not change, and the only mode of heat transfer between the surface and the surrounding is through convection. Okay, so we are required to find out what is the Q coming out of this cylinder. So the equation for finding out Q will be h times Ts minus T infinity, but we don't know what our h is. So to calculate h, we can use the relation of Nusselt number. So because our characteristic length here is the diameter, so the characteristic length is always the length in the characteristic length in the direction of the flow. So we have a diameter as the characteristic length, so that's why the subscript of Nusselt number is T, and we have h times d divided by kf, where kf is the thermal conductivity of the air. So this is air which is blowing over the cylinder. So now we don't know what kf is, and we don't know what the Nusselt number is, and we need to find out a correlation for that. But before that, we need to characterize what type of flow we have. So for that, we need to calculate the Reynolds number. So our Reynolds number will be u infinity d by the viscosity nu, but we still don't know what these properties are. So what we do is uh, we use table. So first thing, we will calculate the film temperature TF. Our film temperature TF will be the average of surface and surrounding temperature, which will be 350 Kelvin in our case. So we have our film temperature, and we'll calculate all the properties at this particular temperature here. And to find the properties, you have to refer to table A.4 in the appendix A, which is behind your book. So this is how the table looks like. So we need the value at 350. So these are the values that we are interested in. Okay, so there's one more thing that you must be careful about while reading this table, is that these parameters here are already multiplied by a factor of 10 to the power 7 or 10 to the power 6. So the way you read these properties, it will be like, for viscosity, you will read that nu into 10 to the power 6 is this value 20.92 here. So your viscosity, you'll read it as nu into 10 to the power 6 equals 20.92. So your nu will be 20.96 into 10 to the power minus 6 meter square per second. Similarly, your K will be 30 into 10 to the power minus 3, which we got from here. So your K into 10 to the power 3 is equal to 30. So K will be 30 into 10 to the power minus 3, and your Prandtl number is given as 0.7. Okay, so we have our thermal and fluid properties from table A.4. Now we substitute these properties in the formula of Reynolds number. We know what our U is, we know the diameter. We substitute in the uh, viscosity, and the value that we get is 4780.1, which is far less than our critical number of 10 to the power 5 into 10 to the power 5. So our flow is a laminar flow. Okay, So now we know that our flow is laminar, so we can now look for a correlation for our Nusselt number Nu. So our correlation for Nusselt number Nu is equation 7.45 in your textbook, and this is what the equation looks like. So your average Nusselt number for the entire diameter will be some coefficient C times the Reynolds number to the power m, Prandtl number which we've calculated at the film temperature to the power n, and there's an additional term which is the Prandtl number divided by Prandtl number at S. So the S here stands for the Prandtl number at the surface temperature. So our surface temperature here is 400. So we'll need to calculate the Prandtl number at that. And then they have given us a condition that your Prandtl number should be within the range of 0.7, and it has an approximation sign here, and it should be less than or equal to 500. So uh, just below the equation in your text, the text says that all the properties are evaluated at T infinity except for the Prandtl number at S, which is evaluated at Ts. So we need to calculate the Prandtl number at Ts. Values of C and M are listed in table 7.4, which we'll look at in a second. And they've given us the value of N. So your Rn will be 0.37 because our Prandtl number is less than 10. Okay, so our Prandtl number from the previous table that we looked, table 8.4, at the surface temperature of 400 is 0.69, and although it says that where all properties are calculated at T infinity, we have actually calculated these properties at film temperature TF, okay, which is a better way of approximating things. So moving on, this is we still need to calculate what we need. We still don't know what our C and M's are. So as the text here says, we have to refer table 7.4. So our table 7.4 gives you the coefficient for circular cylinder in a cross flow, which is what we have here. And we fall in so our Reynolds number was around 4000. So we fall in this third range. So our C value will be 0.26 and M will be 0.6. So now we have our C, we have our M, and we have our N. So we'll substitute, so we'll use the relation of Nusselt number here, and we'll substitute the values of C and M in this particular equation. So our C is 0.026 times the Reynolds number to the power 0.6 multiplied by our Prandtl number calculated at the film temperature to the power 0.37, and the ratio of the two Prandtl numbers divided by 1 by 4, and this will be equal to H d times Kf. So we want to calculate our H so that we can calculate our heat transfer rate, heat flux. So on solving this equation, we get our H as 36.89 watt per meter square Kelvin. We substitute this in Newton's law of cooling. This is our H. Our temperature is in Kelvin, 400 minus 300, and this gives us our heat flux as 3689 watt per meter square. So this is how you approach a problem of calculating the heat flux for a particular geometry. First thing, you identify the geometry, then you identify the flow, you calculate the film temperature, calculate the properties at the film temperature, find the appropriate correlation for the Nusselt number, then calculate the H and then the heat flux.